Starting. 3, 2, 1. And I believe we are live. Hi there, ast111. I'm Frank.
And I'm Alex.
And we're here for our second YouTube live event. And I hope we have a nice agenda for you here. We're going to talk a little bit about who we are and what we do and where we're at. And Alex has some really cool news. Then we'll answer some of the questions that have been posted on the discussion board, and that's not going to fill a complete hour. So Alex is going to present some nifty stuff, and then I'll take over and I'll do a little presentation, and that'll probably wrap us up on our agenda. So let's go ahead and start that. So I'm Frank. I'm the instructor for ast111. I'm the one who posts so much on the discussion boards. I hope you enjoy those posts. Some of them take some time to get together. So I'm a professor here at Arizona State University. That's one thing I do. And I have a lot of fun doing astronomy. And Alex?
Yes, I'm currently a PhD student at ASU. My research revolves around building cameras for suborbital flights. And Frank wanted me to share my news, which is I just got an engineering job at a company in Tucson, Arizona called Worldview Enterprises. So you can look them up online, Google Worldview, and eventually they want to do edge of space tourism by balloon. So it's kind of exciting to get into the company on the ground floor.
That is awesome, Alex. I think that's so cool.
Yeah, it's exciting.
Yeah. There'll be people and there'll be scientific instruments and who knows. Would this be, if you were to do this, is this like a private balloon ride? So it's, one or two of your best buds, or is this sort of like the Greyhound bus in the sky kind of approach, where there'll be hundreds of people on a given balloon flight?
Well, I think that I haven't seen figures for how many people can fit in each capsule, but they're a pressurized capsule, so you wouldn't need spacesuit. And the idea is you fly up with, you actually, for the first flights, they're going to have an astronaut who's the chief pilot at their company right now, this guy named Ron Guerin, who used to land the space shuttle.
Yep.
And you get to fly up, and I think it's about 8 people at a time.
Okay.
Something around that figure. And it's a little pricey for now, but much less than Virgin Galactic, about $75K per seat. And so I'd say it's more like the Greyhound bus in the sky, because unless you buy the whole capsule out, you'll probably be going with some fellow passengers.
Well, it can be a party capsule of some sort. Are they going to serve, pretzels and a Coke?
I hope so.
So what would the length of time up in at the edge of space be? How long will you spend there?
So yeah, the balloons go up to around 100,000 feet, and it takes about an hour and a half to get up there. But obviously, it's a lot more comfortable than a rocket. It just kind of steadily increases in altitude, and then at the top, you get about 3 hours.
Oh wow!
So you get to linger up there for a while.
Yeah. And then it's another hour and a half down. Or they just pop the balloon and you go falling.
Yeah, they actually have. That's the reason the astronaut rides with you, because they have a parasol that's similar to what skydivers use. And so he can actually pilot it back down, and so they launch and land from the same spot, which is cool.
Yeah, yeah, wow.
But the coolest idea I've heard from it is that once they really get going, they're going to explore doing early morning flights before the sunrise, and you could see Earth's Terminator come in as the sunrise from up there. So you get to see the curvature of Earth, all the stars, and then you get to see the sunrise. I think that would be the most cool flight to take.
Absolutely.
So that's exciting stuff.
Photo opportunity.
Yeah.
Wow. Very cool. Well, congratulations on that. I think that's totally awesome.
Thanks.
Let's see. Let's move to some of the questions on the discussion board. Let's see. Where am I at? Okay. Everybody, several questions on why pizza. So I guess I'll answer why pizza. I guess my response to that is why not? uh, just trying to do something a little different. And so the idea popped into my head. Well, why don't we do a series in my kitchen? And so we did, and I'm making the pizza, and I guess the pizza will be done at some point. And so the one that was actually made, I actually made two that day at the same time. And the audio crew and the video crew snarfed them up pretty good. So yeah, pizza just because it's fun and different thing to do. Let's see, I'll take one. Joe Schmo 2. Age of the Rings. Each rock in a Jovian planet ring has a limited lifetime due to collisions, but does the ring structure remain indefinitely, continually losing rocks to collisions, but gaining new ones by gravitational attraction of solar system debris? That's a good question. And I think I'm going to venture that the base answer is we don't really know for sure. The current thought is that the ring system, say, for example, around Saturn, is due to a moon that wandered in a little too close. It's called the Roche limit. And basically, at the Roche limit, the tidal force of gravity is greater than the tensile strength of rock. And that means that whatever wanders in there is going to break up. And so it's probable that the rings of Saturn and the other gas giants are due to bodies that wandered inside the Roche limit and broke up. And if that's true, and then each particle doesn't last very long as it continually gets ground down to dust, eventually gravity does take over, and those dust particles or the larger particles will get scattered and make their way down to the planetary surface. So the current estimates are that planetary rings don't last very long, perhaps 50 million years, 100 million years, before they're ground to dust and they fall back onto the planet. So if that's true, we happen to live at a special time with regard to the spectacular rings of Saturn. Whether they get replenished from other moons wandering in or other bodies that can be captured, we don't exactly know yet. But at face value, rings don't last very long. Ring systems are not permanent by any manner of means. Why don't you take one, Alex?
Okay. The one I was going to take is by Ryoko-san. I think I pronounced that correctly, but they ask, I have a question that could either be answered on the forum, either on the live stream. How do we differentiate meteorites from asteroids? So I had an idea of how to differentiate the two, but I looked it up, and the official astronomical society definition is that an asteroid is a planetary body that's 10 meters in diameter or larger. And these are usually found in the orbits between Earth and Mars and what's known as the asteroid belt. But a meteorite, this is when you have to be very careful because these definitions are very specific. In orbit around Earth might be little planetesimals or particles left over from comets that create meteor showers. A meteor is actually a little piece of dust or an object that enters our atmosphere and starts burning. And then it continues to be classified, and there's something called a bolide. That's a fireball that explodes while it's going through the atmosphere. And then finally, it can only be called a meteorite if it makes it all the way to Earth's surface.
Right.
And so the small pieces that make it to Earth's surface are meteorites. So I hope that answers your question. It's tricky classification. And then I think the last part of the question here is, how can we be sure by counting the asteroids out there and naming them that the same one didn't get several names? Since they are regularly crashing on the planets, is it possible that before the sun comes to die, the galaxy will run out of them? So that's a good question. So we're counting the asteroids out there, and I would say that we're not accidentally counting the same ones twice, because these bodies are actually very, very, very spread apart. Unfortunately, in diagrams of our solar system and in movies like Star Wars or Star Trek, asteroid belts are depicted as a bunch of rocks that are extremely close together. This is not true of our asteroid belt. We regularly send probes through the asteroid belt, and there's little to no chance of them accidentally impacting something, because space is big and these bodies are really, really, really spread out. So I think that it would be very unlikely that an asteroid was accidentally counted twice, just because they're typically so far apart from each other. Also, you asked, since they are regularly crashing into planets, is it possible that before the sun comes to die, the galaxy will run out of them? I wouldn't think of this question on the scale of the galaxy, but in our solar system, in terms of our solar system, I would say that I don't think that we will run out of them, because number one, there's so much material in orbit around the sun when our solar system was created, so much that I don't think we'll ever, some of it will never deorbit and crash. And then you'll have to think that there's still material being created by certain big collisions with moons and planets that actually creates more material. So this material, these asteroids, these planetary bodies are continually getting eaten up and combining, and then also being created. So I'd say that we wouldn't run out of them. What would you say, Frank?
Yeah, yeah, I think that's right. They're in orbit, and unless something takes them out of their orbit, they're just going to continue to orbit. My impression would be, even as the sun ages, you're simply going to move and expand. So when the sun gets a little bit older, it will get larger, and some of those asteroids will destabilize and go into the sun. But in general, you're going to start moving objects around, and I don't think you'll ever get rid of all of them. I think on one of the modules, or some of the course material, I posted some links to some very cool movies of the rate of discovery of objects in the asteroid belt that spans about 30 years. It's got a really groovy soundtrack. And you can count or watch as the number of asteroid discoveries increases over 30 years. And they're color-coded by the type of asteroid they are, what their particular orbits are. And if I remember the number right, don't quote me exactly, but I think the number of known counted objects is on the order of about 500,000 these days. And at 500,000, I mean, there's more people than that in the world. And we seem to count people pretty well. So I really doubt there's any double counting at levels of 500,000. That takes a computer less than a second to scan or so. So probably not double counting. But yeah, and to loop back to the original part, yeah, I kind of agree with you, Alex. I don't think we'll ever run out of them before the sun actually meets its final fate. Cool. Let's see. I'll cover one question, and then we'll let Alex get some nice stuff on Cassini. A couple of questions on various aspects of Big Bang, and I'm kind of going to punt on that, not because it's not an interesting question. It is. But this is a class in solar systems, and I want to keep the scope of the class and the focus of the class on solar systems. On the other hand, every week, in the additional resources for every week, if you click on that, there'll be a link in there to a brand new free textbook that covers a lot more than solar systems, and in part they will cover cosmology, cover Big Bang cosmology. So some of the questions that were asked can be have some light shed on them, so to speak, from taking a look at that free textbook on what they have to say about the expanding universe and other questions associated with cosmology. Let's see, I think that pretty much covers the questions that were posted on the discussion board. So let's move into the next phase. We're going to do some presentations. If you have questions, if you're watching, you can still post questions on the discussion board. I'll be monitoring those as we go through. So Alex, why don't you take it away?
All right, I prepared a presentation on the Cassini mission, which is still in orbit around Saturn. So let me bring that up on my screen here. Okay. All right. Is that showing up? Okay, just a second. Technical difficulties. There we go. Okay. So, excuse me. So for those of you who don't know, Cassini is, in my personal opinion, one of the most successful planetary exploration missions of all time. It got to the Saturn system in 2004. It's been exploring ever since, giving us great images and other data from the planet itself, Saturn's amazing ring system, and all of Saturn's incredible moons. And so let's go into that a bit. A little bit of a background. Cassini launched in October 1997, so quite a while ago, from Kennedy Space Center. Here's a, you can tell this is from the 90s. This is a diagram showing Cassini's path to Saturn, and a technique often used by NASA to get a lot of mass to the outer solar system, and it saves a lot of fuel, is to do gravity assists. So Cassini was launched from Earth. It actually went to Venus, did a gravity assist from Venus, then did an assist from Earth, another assist from Venus, Earth swing by all the way out to Jupiter, and then finally all the way out to Saturn. So it took 6 years to get all the way out to the outer planets. They didn't turn many of the instruments on when it went by Venus, but they got some, Cassini took some cool preliminary images at Jupiter. So this is still one of the best Jupiter planetary images we have, taken by Cassini. And this is a cool video of one of Jupiter's moons called Io that actually has active volcanoes all over its surface. So those bright dots are actually active volcanoes that were imaged by Cassini. So some cool Jupiter data from Cassini. But in 2004, Cassini got to its primary target, Saturn. So this is one of the first images in 2004 that it saw. And you could already tell that we were in for an amazing mission just because, I mean, wow, it's such a cool planet to see. A little bit about the Saturn system itself. Saturn has over 60 moons, so we won't be talking about all of them, but we'll talk about a couple of the main ones. And one of the most prominent moons here is Titan. Titan is an enormous moon, one of the biggest in the solar system, and we'll get into that later. But Saturn's such an interesting place because it has such a rich variety of bodies in orbit around it. Cassini itself, here's a diagram of what the orbital tracks over the years have looked like. So much like Cassini got a gravity assist on its way to Saturn, Cassini used the rich moon system of the Saturn system to use little miniature gravity assists and change its orbital path by passing near Saturn's moons during its journey. It also had a decent amount of maneuvering fuel. So all these orbital paths were a combination of using maneuvering fuel and doing gravity assists over the years. And so first, let's look at some views of Saturn that Cassini saw. So uh, here's the planet itself. It's got this rich ring system. And something that is worth pointing out is that Saturn, in these rings are thought to be made up of billions of particles of ice and dust. And what was discovered by Cassini is that these actually scatter light really well. And on the night side of Saturn, you can still see the planet really well, illuminated by what they call ring shine. So even the night side of Saturn is kind of glowing from light being scattered to the ring by the rings onto the night side, which is cool. And then you've got this really awesome dark shadow that the planet itself casts over its own rings. This is actually from Hubble. Saturn was discovered to have prominent aurora, much like we have on Earth. And this is caused by a planet's magnetic field interacting with solar particles. And it's worth pointing out that here's a cool video from actual data taken by Cassini. These are stars going by in the background. And this is a colorized actual data of aurora seen on one of the poles of Saturn by Cassini. So Cassini was able to image auroral patterns, which is cool. Moving on, here's another cool picture. There's Saturn's dark shadow cast over its rings, and you can see that the night side is lit up by that ring shine I was talking about. And as I go through these images, pay close attention to the rings. They're very, very dynamic. And for the first time, they were explored in great detail by the Cassini mission. And so you can see that in certain areas, there's gaps where there's apparently no ring material. And in other areas, you'll see wave-like patterns. And so we'll get into the reasons behind why the rings are so dynamic looking. There's just another interesting artistically placed picture, and you can actually see the shadow of Saturn's rings cast back on the planet. Same thing, this is from the night side of Saturn with some ring shine present, and you can really see the scattering of light through the rings well here. There's Titan, again from the night side, both crescents. And then this is an interesting perspective. Cassini has taken a lot of pictures of Saturn edge on. So you can see that the rings of Saturn are not necessarily quote unquote big, thick looking rings. It's a very skinny equatorial region of material. And Saturn has so many moons, you can almost always see some in the foreground or background whenever you see a picture of the system. Here's one of the coolest yet most confusing pictures. This is actually the body of the planet in the background here, this blue looking region. These are the giant shadows cast by the rings. There's the moon in the foreground, and here's the actual rings in the foreground. And you can see really well here how you can see there's separations of ring material, there's gaps within the rings, and there's even little wave-like structures in the ring material. One image with 3 rings or 3 moons visible. Very cool. And another cool thing that fortuitously happened while Cassini was taking data of Saturn is that a giant storm developed. I think this was back in 2011. We can image Saturn from ground-based telescopes and the Hubble Space Telescope, but Cassini is so much closer to Saturn than our telescopes are. Its resolution is just fantastic compared to Earth-based observations. So it was really awesome that Cassini got to image this storm in detail, because this storm cropped up, and then I think it was just a matter of weeks or months later that the storm disappeared again. So this type of upper atmosphere storm on a gas giant like Saturn is still being studied by planetary scientists today. Here's another overhead image. This is purposely overexposed. You can see the shadow of the rings on the planet, purposely overexposed so you can really see that ring structure. And then I like to focus in on something else that was discovered by the Cassini mission, which is the North Pole is actually this giant geometric shape. It's a hexagonal storm on the North Pole of Saturn. So here Cassini zooms in closer and closer, and you can see it's kind of a hexagon shape with a storm in the middle. And there's some theories to what processes happen in Saturn to create this shape. But like I said, if you're a potential planetary scientist or just interested in planetary atmospheres, objects like this, dynamic objects like this, are very fascinating to try to understand. And then these are just some great images, some of the most close-up images that Cassini got of this particular storm. You can actually see cloud structure, and then you can start to make out depth. So these clouds are higher, and it goes lower and lower. Almost looks like an Earth hurricane, except I will say that the size of this hexagon is about the size of the diameter of Earth. So a little bit bigger than what we'd experience on Earth. Matter of fact, the size of our planet itself. And here's an even closer image where you can see a lot more of the cloud structure. Very interesting. And finally, by piecing together images in succession that Cassini takes, we can actually make movies, and you can actually see the cyclonic rotation of this storm. And it's interesting, in the middle here, you can see the storm going around in a counterclockwise direction, and you can see the exterior clouds going around in a clockwise direction. So very interesting stuff going on. Okay, so let's get a little bit more into the actual ring dynamics of Saturn, which I was alluding to earlier. So here's a close-up of the rings, and if you look very closely down here, you actually get what we call a shepherd moon. So these are very tiny moons that actually orbit within the rings themselves. And the gravity of these moons actually create gravitational waves across the ring material as they orbit by them. So here in this picture, we have a shepherd moon, and you can see the sun is shining from the bottom of our screen up towards the moon, and you can see the moon's shadow over the rings, and you can see the waves being formed gravitationally behind the moon, with shadows being cast by that disturbance, and you can see waves being formed in front at the leading edge of the moon. So you can start to understand this whole gap in the rings was cleared by this particular shepherd moon. And then shepherd moons, or gravitational resonances with moons that orbit further out, are what are responsible for all these interesting waves and shapes you see and intricacies you see in the rings of Saturn. So here's kind of another cool image. There's a moon disturbing the ring system in the exterior of the rings out here. And then here's a moon that orbits in this giant gap, and you can see it's kind of creating waves and folding the interior edge of the ring up at the top of your frame. There's a closer up picture. And then I have a little video of this as well. So you can see how, as the shepherd moon goes by, the gravitational interaction with the rings. So they kind of fluctuate and then they settle. You can watch that one more time as it goes by. Really cool physics going on there. And this is one of the most high resolution images of this type of wave interaction with the ring material. And what's really cool about this image in particular is that since Cassini is now near the end of its life, it's getting more and more brave with getting close to the rings. Because guess what? Cassini, relative to Saturn, at times, especially when it's close to the planet, is traveling relative velocity around 70 to 75,000 miles per hour. So that means even a small piece of dust could almost act like a bullet if it was to impact the spacecraft. And so for most of the mission, since it got there in 2004, they've been conscious of this and tried to orbit really far away from the planet while it was taking data. But they're getting braver and braver and bringing Cassini close. And in this image, Cassini will never get close enough to actually see the individual particulates that make up Saturn's rings. But this graininess here is not an error in the image. This is actually, you're so close to the rings, we can actually start to see some of the individual structure of the ring material itself. So the ring system of Saturn is very, very interesting stuff. And the Cassini data is going to help scientists try to understand this for probably years and years to come. One of the most interesting Shepherd moons, this has come to be known as the ravioli moon. This one was imaged very recently too. So here's Saturn's rings on either side. And there's this moon that's called Pan, which looks kind of like a ravioli. So here's an image of Cassini approaching and then departing Pan. And you'll notice that the ravioli shape, it looks almost like a moon that has a ridge that's been formed around its equator. So here's some close-up images of it. And in planetary geology, this is not always the case, so you have to be a little careful, but there's a rule called superposition, where on the moon itself, you can see some craters, you can see some wrinkle ridges, you can see some what look like faults, maybe a canyon. So this area looks like it's gone through some geologic stress over the years, and because you see so many features, it's safe to assume that this might be older structure. And then look at that equatorial ring, and you can see how smooth it is. There's not really any asteroid impacts I can see, and it's safe to assume that this material is much younger. So the current theory for this moon is that this structure is formed since it sits within the rings of Saturn. The actual ring material is depositing on the equator of this moon and giving it its own little equatorial ring of itself. So this material is thought to be much younger than the actual bulk central part of the moon itself. Okay, so we can't talk about Saturn system and not talk about Titan. Titan's one of the most fascinating objects in the solar system. It's the only moon that has an atmosphere, and you can see it's larger than Earth's moon. So you cannot see what's under Titan's haze if you're trying to image it, and if you were looking at it with your eyeballs, you wouldn't be able to see anything except this thick cloud layer. So here's a nice image of the atmosphere edge on. But Cassini is able to pierce through the clouds and see what's underneath by bouncing radio waves off the surface. And what Cassini's discovered is this rich system of rivers and lakes. And it looks a bit Earth-like, but the difference is that Titan is extremely cold, very far away from the sun, and these lakes are actually made out of liquid methane. So while on Earth we have water ice, we have water in the form of clouds, water vapor, and we have water in its liquid form. And it's very similar. They have methane ice, methane liquid, and methane clouds. And so here's a close-up of a radar image showing a methane lake, methane streams that can flow through these canyons, and then here's the rocky surface. One of the coolest aspects of the Cassini mission is that right when it arrived, it had a little probe called Huygens attached to it, and that probe was actually sent down to Titan successfully and took images on the way down, and then it snapped off an image when it landed on the surface. So this is kind of what the landscape of Titan looked like as the Huygens probe was on its descent phase. So you can see some of these stream beds of methane and its rocky surface. And then this is the only picture we have of a moon in our solar system outside of Earth's moon. So you can see very clearly that the rocks are rounded here. So it was thought that this might have used to be an old stream bed of liquid methane, because that could explain why these rocks have been smoothed over time. So very fascinating. Titan is another place where scientists are very interested in looking for the potential of life, just because it's such a unique mixing pot of so many different elements. And then another one of the moons that we can't talk about Saturn without mentioning is Enceladus. So here's Enceladus. It's much, much, much smaller than Titan. It's essentially just a big ball of ice. Here's a size comparison. It's about the same size as England. So we're talking about a very small planetary body. Here's a picture of a crescent in the background. There's Saturn. So Cassini's taken some very fascinating pictures of Enceladus. But in this image here, you can see the day side of Enceladus is lit by the sun, and the night side is actually lit by ring glow. So you can clearly see the night side, and then start focusing in on the south pole of Enceladus here. Something's going on. And this is one of the most high resolution pictures ever taken by Cassini of Enceladus. So this is all ice. And you will notice this really prominent canyon looking feature that runs down the middle of the image. What these have been come to known are the tiger stripes of Enceladus. And the interesting thing about the tiger stripes is that they have water geysers coming out of them. They're constantly spewing water, and Cassini actually discovered this feature on Enceladus. They're in the south pole of the moon, and what this implicates is that the moon is covered in ice, and underneath there's an ocean of water. Here's a better picture of the tiger stripes spewing water into the Saturn system. And what was actually discovered, Cassini actually flew through these water features and was able to get some of the elemental composition. And interestingly, the spectroscopic composition of the water matched very closely to the composition of Earth-based hydrothermal vents. So way deep, deep, deep down in Earth's oceans, we have hydrothermal vent systems, which are actually water being heated by the core of the Earth. And we have whole ecosystems down there that are surviving without the use of the sun. So this immediately became a place of interest for scientists who are searching for life, because Enceladus has its own heat source in its water ocean that could potentially incubate life. So it's a very, very dynamic, interesting place. Okay, so now we get into the sad part. Cassini is actually on its way out in what NASA is calling Cassini's grand finale. We mentioned that Titan and Enceladus are two places that scientists believe that life could be evolving on. And so there's a thing in NASA called planetary protection. And since Cassini's been going around Saturn since 2004, it's essentially at the end of its maneuvering fuel. And to make sure that Cassini doesn't crash into either Enceladus or Titan, they've decided to purposely crash Cassini into Saturn to keep any Earth microbes from accidentally getting on Titan or Enceladus. And so here's an animation, and what Cassini's actually doing this right now. It did its first one of these orbits actually yesterday. It's going to do a number of orbits in between Saturn's rings and the planet itself. This was not done previously in the mission because this is a very risky maneuver. It's known that ring material is constantly falling into Saturn. So Cassini is doing these orbits. What it will get is Cassini will be very close to the planet at these times, and it'll get really close pictures of the clouds. So to try to protect the spacecraft, as I mentioned earlier, when it's close to the planet, it's traveling around 75,000 miles per hour. They actually angle their Cassini's big antenna dish in the direction of its motion, in the hope that if it hits any of the ring material, it will be absorbed. The impacts will be absorbed by this dish, because that'll basically any rock or dust will be like bullets that are being shot into Cassini. And in order for Cassini to complete these orbits successfully, this dish needs to absorb those impacts to protect the sensitive instrumentation, especially the cameras, the computer, etc. So this is really fascinating, and this is hot off the press from yesterday. These are pictures that were just taken of Saturn's upper atmosphere, and these are raw. This is raw data that was just returned, and these are the closest pictures of Saturn's atmosphere ever taken. And so every time it does this, it's going to get closer and closer to Saturn. So we'll continue to get more and more interesting, detailed pictures of Saturn's upper atmosphere and cloud dynamics. And so the actual final impact is going to take place in September. So mark your calendar, September 15th. And the cool thing is that Cassini is planning on taking pictures right up to the bitter end. So even after, as it's entering Saturn's atmospheres, we'll hopefully get some really amazing, closest ever pictures of Saturn, and it'll keep transmitting until it dies. So it's going to be interesting, and Cassini, it's already given us so much data and so many amazing images, and it's just a cool mission that it's going to continue to give us images till the bitter end. So thanks for listening to my presentation, and talk to me on the message boards if you want some more information on Cassini or some resources. If you want to access any of the pictures that I just showed online here, they're all publicly available. And one really good website is a website put out by NASA called JPL Photojournal. If you just Google that, you can see all of NASA's solar system pictures that have been taken throughout history. So that's a really fun website. And I'll leave you with this. One of the coolest pictures taken by Cassini. It's being backlit by the sun. And if you look in the bottom right-hand corner here, zoom in, you can actually see the Earth and Moon system from about 745 million miles away. So really puts everything in perspective, doesn't it? All right, thanks, guys. And I will stop sharing my screen.
That was cool.
Thanks.
I hadn't appreciated that they were already doing the orbital death march yet.
Yeah, they've begun. I wasn't aware that it was going to... I thought when they started the final orbits, it wouldn't take a matter of months. I thought it would be a lot faster.
Yeah.
But it's cool. It's cool that it'll go till September.
Yeah. Wow. That is awesome. Yeah, Cassini's been a fantastic mission. Yeah, maybe you should put a link to that presentation on the discussion boards, put it on Dropbox or something along those lines. Put it in the cloud somewhere where people can grab it. It's pretty cool. Okay, we have about 18 minutes left. I didn't see any new questions come in, so I'm going to do a short presentation on time. So let me pull up, and I'm going to share screen. Okay, and I'm on there. Start screen share. Do you see that, Alex?
Sorry, Frank. It went away.
Went away. Okay. How about now? Okay. Start screen share. Got it. It doesn't like full screen.
Oh, gotcha.
I went into full screen mode. And...
There it is. I see it.
Okay. Right. Okay. Well, we'll just go with this. Okay. I want to talk a little bit about time. And so my opening quote is from John Steinbeck's novel, The Short Reign of Pippin IV. The passions of astronomy are no less profound because they are not noisy. And the story is about Pippin, Herstal Pippin, who's an astronomer, an amateur astronomer. And in one of the only political satire humor books that Steinbeck wrote, Pippin becomes the king of France. And he really doesn't like it because he can't get to his telescope often enough. So he will frequently dress as a commoner, as shown on the cover of this particular image, get on his scooter and get away so that he can enjoy the passions of astronomy. And in the end, he gets his wish of being dethroned the king of France, and he can enjoy his passion a little more quietly. It's a short little book. If you ever get a chance to read it, you like stories about astronomy, it's a nice one to read. Go check it out. So I want to talk about time through the ages. This is just a lovely piece of artwork on mechanical clocks and stars. in particular the Big Dipper here, and that's exactly exactly what the point's going to be: mechanical clocks versus what the sky says. Okay. So 'tis the season. So agricultural dependence meant knowing when to plant, when the first frost was. Everything is dependent on the sun and what time and what season the sun says. But as societies grow more complex, they tended to desire fixed dates for things as when is my birthday? When do I have to pay my taxes? When is the 4th of July, such as the image here in Tempe? And as soon as society wants to start doing that, as soon as you want to start keeping fixed dates, this introduces the difficulty of keeping the seasonal calendar, that is the time that the sun says, versus your man-made human calendar synchronized. So you've got something, you want to impose a time system, and the sun has its own time system, and keeping those two in lockstep is the challenge. Okay, and that challenge is going to take us all the way up to the modern era. So just for reference, as we go along, the seasonal year is defined from vernal equinox, so that's the spring equinox, which we just kind of went through, to vernal equinox, and it is about 365 days, 5 hours, 48 minutes, 46 seconds, or 365.2422 days. And since we're going to be talking about clocks and keeping them synchronized and how they become unsynchronized, I sort of liked Dolly's persistence of memory image here. So the yearly calendars, originally, going back into the few thousand BC, were often based on summer solstice to summer solstice. So that defines where the new year to new year, or when a particular star first rose with the sun. The image here is an example of the star Sirius, which is in the constellation Canis Major, just as it's rising with the sun. So on the left is the sun just about to pop over the horizon line. Sirius has already popped over the horizon line. And this is known as a helical rising, when a star rises with the sun. Okay, so the helical rising of Sirius. And the Egyptians used Sirius, which is a natural thing to use because it's the brightest star in the sky. And it rose in early July when the Nile was in flood. And with an agricultural economy based on the Nile flooding, the helical rising became the most important day of the year. And hence, it was sort of natural for them to make that day one of the year. So their days began in early July with the helical rising of Sirius. Now Sirius, as I mentioned, is the brightest star in the constellation Canis Major, and it's sometimes called the dog star because Canis Major. And it is from this time period, several thousand years BC, and the Egyptians' use of the helical rising of Sirius in early July is where we get the phrase, the dog days of summer, right? So it's the helical rising, the dog constellation, the dog days of summer. Another example of conventions used in timekeeping in astronomy persisting through millennia to the present day. The image here is from Uranographia from John Hebilius on pictures that one can draw in the sky based on the constellations. So that was year to year. That's a little bit long. And so people wanted to break that year up, however it was defined, into smaller time increments. And so how do you mark intervals within a year? And so the first marker, the obvious marker to use, is the moon. And in fact, that's the root word of the word month. Month, moon, you can see where that comes from. And again, quite old use of the month. But there are two main obstacles with using the moon to subdivide a year. The image here is the Aztec calendar stone, and the Aztecs used a lunar-based yearly calendar. So the first obstacle is that the lunar month varies between 29 and 30 days. And this variance is due to the visual appearance. This is called the synodic period rather than using the sidereal period. And the synodic period is the time between identical sun, moon, and object alignments. So, for example, full moon to full moon. It's easily observable, full moon to full moon, but it's not too useful because it's an apparent period. It depends on your viewing position. It's not the real period, it's just how things appear to look. The real period is called the sidereal period. In fact, it's even got the word real in it, sidereal. So that's kind of a mnemonic to remember. This is the one that matters. And this is the time between identical star, Earth, and object alignments. This is the period that you would stick into Kepler's third law or Newton's generalization of Kepler's third law. But it's harder to observe. It is not trivial to observe what the real period is, the sidereal period is. And so let's do a little graphic on the difference between those two. So let's put everything on the line to start. So we have the sun on the left, we've got the Earth, we've got the moon, and we have a distant star shown on the right. And so we'll start the clock here with everybody aligned. The moon is in the full moon phase because we got the sun, Earth, moon, and we're going to start spinning the Earth around its orbit and let the moon go. So the time will go on. Earth will go through its orbital period. The moon will orbit around. And at some period, you're going to get, at some point in time, you're going to get the same Earth, moon, star alignment. And the time to reach this is the real period. This is the sidereal period, and it is 27.322 days for the moon. But the moon is not in a full moon position. It has to be opposite the sun. And so you have to wait a little bit more time for the moon to travel that extra distance simply because the Earth has moved around in its orbit until it gets to the full moon phase again. And it's this time period that is variable. It goes between 29 and 30 days because the Earth's orbit is not perfectly circular. There's some variation. It goes a little faster at some point in its orbit and a little slower at other points in its orbit. So it varies around a little bit. And it's fundamentally that difference. Okay? So that's a little bit about the synodic and sidereal differences. The second pragmatic obstacle to using the moon is that the year can't evenly be divided by sort of the average lunar month of 29.5 days. 12 lunar months would be 11 days too short, and 13 lunar months would be 19 days too long. And so if you base your calendar on the moon, your entire calendar is based on the moon, you're going to get out of step with the seasons. So if you don't make any adjustments over time, then the hottest time of the year is eventually going to be taking place in what would normally be the winter months. And so many cultures got around this by inserting an extra 13th month every few years. And the whole point here of this is to keep my desired man-made calendar with the timepieces in the sky, whether that be the sun or the moon. So this problem of synchronization of those two is going to continually keep happening. Okay. Oh, and just on the aside, since we're talking about moons, it was accepted practice in Babylon about 4,000 years ago that for about a month after a wedding, the bride's father would supply his son-in-law with all the mead he could drink. And mead is a beer. It's a honey beer. And since the Babylonian calendar was lunar-based, this period was called the honey month, or what we call today the honeymoon, after a wedding. So again, millennia old, originating in astronomy. And the moon, of course, has many names and items associated with it, like it's where the word lunatic comes from. We get a blue moon, a wet moon, harvest moon, and on in common culture. The Egyptians were the first ones to give up on using the moon to mark time within a year, and they took a more radical approach. They are the ones that divided the year into 12 months of 30 days each for a total of 360 days. And at the end of the year, they added 5 days for an approximation of 365 days. Now, even the Egyptians knew that 365 days was not completely right. In order to keep their clock and the sun's clock synchronized, extra days were kind of randomly added to keep the two synchronized. Okay, so that lasted for a while, and then the Romans come along, and originally the Romans had a surprisingly messy calendar. A year was 10 months long, with March being the first month. And extra days were inserted at random in different locations to keep the seasonal and calendar year clocks together. So in one part of the Roman Empire, it might be one time and one day. In another part of the Roman calendar, it would be another time and another day, because they had chosen to insert the day at a different time. And so that's kind of a very messy calendar. But nevertheless, parts of the Roman calendar are still with us. September, October, November, December. And if you know any sort of a Latin language, you recognize that as 7, 8, 9, and 10. Those were the 7th, 8th, and 9th, 10th months in the Roman calendar. They're no longer the 7th, 8th, and 9th, and 10th months in our modern calendar. They're offset by 2, but nevertheless, we keep the names from the Roman calendar. So a complete mess. Everybody kind of doing what they want locally with the calendar, and that was just unacceptable. So 1 year before his death is Julius Caesar instituted a new calendar. We're going to have 12 almost equal months. March is still going to be the first of the year, totaling 365 days. But then he institutes the new rule that every 4th year, or leap year, 1 extra day would be added at the end of the year. Okay, so if March 1 is the beginning of the year, that means the end of the year is February 28th. So this would give an average of 365.25 days. That's a much better approximation. Everybody in the Roman Empire all has to add the same extra day at the same time. You don't get to choose anymore. But this is the origin of the leap year. Right? It originates with Julius Caesar, and it being added at the end of February also originates with Julius Caesar. And so Julius liked his new calendar so much that he decided to take one of those 12 months and name it for himself. And that's where July comes from. July is for Julius Caesar. And money likes power, power likes money. And there was a powerful family at the time, in Julius's time, known as the Juno family, who was a benefactor to Julius. And so he decided to honor his benefactors by giving them a name of a month. And so Juno became the month of June. And so June and July go all the way back to Julius Caesar. And of course, now the pattern was set. You had a Roman emperor who took a name of a calendar, and so every Roman emperor after Julius had to take a month and name him for herself. Unfortunately, the vast majority of those did not stick, but one that did stick was Julius's grandson, Augustus Caesar. August, that's where the name August comes from. So our summer months, June, July, August, all come from the Roman Empire and the emperors. Now 365.25 is close. It's only 11 minutes too long, or 1 day in 130 years, or about a week after 1,000 years. So who's going to worry about that, 1,000 years? Well, guess what? 1,000 years goes by. And so by 1582, the seasonal and calendar years were about 10 days out of sync. And this was getting pretty noticeable. And so take a look at this calendar of October 1582, and you'll notice something strange. October 1, 2, 3, 4, 15. So the first thing that Pope Gregory does is he chops 10 days out of the calendar so that we can at least get things synchronized again. This created near social riots What if my birthday was October 6th? What happens to my birthday? Did I have to pay taxes? Did I get paid? You just chopped a week out of the calendar. I'm supposed to get paid every week. Do I not get paid that week? Anyway, huge amount of unrest. Anyway, they get over that. They get through it. The clocks are now resynced, and it is with Pope Gregory that the shift is made from March being the Ides of March being the first of the year. This is where January 1 now starts to become the beginning of the year. And every 4 years, an extra day is added in February, just like Julius. So far, there's no change. It's the same system. We just change the origin point from March 1 to January 1, and we still have leap years. But now Pope Gregory adds the next correction, so that century years divisible by 400 are leap years. So for example, 1700, 1800, 1900, these are not leap years, and so we don't add an extra day. But 1600 and Y2K, year 2000, are leap years because they are evenly divisible by 400. And so this next correction to the system is only 38 seconds too short, or about 1 day in 2200 years. So this is the modern calendar that we have right now, and almost. Except, what are we going to do? Are we going to repeat the errors of the past and wait another 2200 years before the clocks are out of sync again by a day, or 22,000 years and wait until the clocks are out of sync by 10 days and have to go through a giant upheaval again? No, no more. So the modern year, the clocks are corrected twice a year. 1 second is added to the calendar clock at midnight on either June 30th or December 31st, when the difference between our desired clock, our calendar clock, and what the clock that the sun and the rotation period of the Earth say reaches 1 second. So we're never going to let the clocks get out of sync again by more than a second. And so the calendar clock is maintained with atomic clocks, that's done in France, and the seasonal clock, which is largely based on Earth's rotation rate, which is variable and slowing down, is done by the U.S. Naval Observatory, and that's their stunning architecture of their building shown in that building. That's where Earth's rotation is most precisely measured, and hence the period of the year. So this is our modern year. So one other point, which I think we made earlier in this course, is why are there 7 days in the week? Where does that come from? And there are 7 days in the week because there were only 7 objects that were known to move on that otherwise immutable celestial sphere: the sun, the moon, Mercury, Venus, Mars, Jupiter, and Saturn. And so each one of those was so special that they got their own day. And our particular names come from the Norse Celtics. So we got the obvious Sunday, Moon Day, Tuesday, Mars, Woden Day, Mercury, Thor Day, Thursday, Jupiter, that's today. Today's a Thor Day. Freya, Venus Day, and then Saturn Day. So that's the days of the week. How about time zones? Where did time zones come from? Where'd that ever happen? Well, it used to be that before transportation became a big deal, is that every location would set properly its time from the local astronomical conditions. So the time in Tempe, Arizona would be different than the time in Flagstaff, Arizona, or Tucson, Arizona, because they have different locations. And that's fine, that's absolutely proper. But on the other hand, if you're traveling, it makes it really hard to know when trains or eventually airplanes are supposed to arrive and depart. Are you using the local time, and how do you calculate that, and whose local time? Big mess. So as with the trains, the railroads that introduced the 4 time zones in the United States in order to standardize the schedule. And so in 1918, the US Congress made the rail zones official in the United States. You notice the zones are not straight lines either. They are various geopolitical realities, geography boundaries to go around. And then that was picked up by what the forerunner of the United Nations was, and the system was instituted worldwide. And so so it's basically from transportation is where we get time zones from. And that's what I wanted to say about time. And there's a little art piece clock on the sidewalk to let you go. So we went a little bit over. We're about 5 minutes over. I'm done there, so let's get out of there. Stop. So I went a little bit over, but that's okay. And with that, I think we should probably say goodbye. So I want to say goodbye. I want to thank you very much for taking this course, and I will be sending around a final message here in a day or two. And cool. Alex, good luck with that new position. I hope it works out fantastic for you, and I hope you get to take one of those rides yourself.
Oh, I hope so. I'll also post my presentation, a link to the discussion board.
Okay, cool. All righty. Thank you, everyone. Bye-bye.